Every time you run a load of laundry, you're essentially unleashing a horde of weaponized microscopic assassins into your washing machine.
Right, which sounds so dramatic, but it's literally what's happening.
Exactly. I mean, we treat this like a totally mundane chore,
Yeah.
just pouring a little blue cup of liquid over our clothes. But what is actually happening in that water is it's a hyper-targeted biological disassembly.
Yeah, complete molecular
And
breakdown.
today we are opening up a document. It's simply filed as 112116.pdf, and it totally pulls back the curtain on this exact kind of invisible machinery.
It really does. It's fascinating.
So our mission for this deep dive is to decode this biochemical cheat sheet for you. Because it turns out the exact same molecular mechanics that obliterate like a pizza stain on your shirt, those are also responsible for the sweetness of your ice cream.
Oh, yeah. And the structure of your breakfast.
Right, and the fundamental defense mechanisms keeping you alive.
It really is the ultimate backstage pass to the physical world, honestly. What we have in these sources, it isn't just a list of abstract biological concepts.
No, not at all.
It is a mechanical breakdown of how human bodies and modern commercial industries operate right down at the molecular level.
Which is just, it changes how you see everything.
Exactly. It's about looking past the macroscopic things we interact with every day and, understanding the microscopic physics and chemistry that actually make them possible.
Right, because once you understand the underlying mechanisms, the world looks completely different. So we're going to trace this architecture from the ground up today.
Step by step.
Yeah. We'll start at the absolute center of human life, looking at the genetic vault of DNA and the molecular machinery that translates that code.
The blueprints, basically.
Exactly. And from there, we need to understand how that data physically manifests into the proteins that actually build us.
Right. And how a very specialized class of those proteins enzymes have been hijacked by human engineering to run our factories.
Which is still blowing my mind. And finally, we'll examine the chemical architecture of the fuels powering the whole system.
The carbohydrates and lipids.
Yes, and the incredibly delicate regulatory molecules we call vitamins, which govern the entire metabolic engine.
So it's basically a journey from pure information to physical structure, and then to the energy and regulation required to keep that structure animated.
Perfectly said. So if we're starting at the level of pure information, we really have to go straight to the nucleus of the cell.
Right to the center.
Yeah. Before we can talk about digesting food or building muscle, we have to look at the original blueprint, which is nucleic acids.
The foundation of it all.
Exactly. And the source text breaks this down into two molecules that, we've all heard of, but we rarely understand mechanically, DNA and RNA.
Right. So deoxyribonucleic acid
Yes.
and ribonucleic acid.
Yes.
And the document establishes DNA's primary biological role with a very specific structural definition. It is an incredibly long, double-stranded molecule.
Double-stranded, which is key, right?
Yeah, it's totally key. That structure is entirely deliberate. It acts as the ultimate vault, storing and passing genetic information to the next generation.
So it's not just a random shape.
No, the double-stranded nature means it has a built-in backup mechanism. The two strands are complementary, and they're held together tightly, which protects the delicate sequence of bases on the inside from, chemical degradation.
Wow, okay. So it is built for extreme stability. It's like the permanent archival record.
Exactly. It's the master copy.
But what really jumped out at me in the source text is the profound medical implication of this specific function. The text explicitly states that cancer is fundamentally caused by damage to the DNA.
Right.
Or by interfering with the mechanism of its replication and how it passes information.
Which completely reframes how we should think about the disease, honestly.
How so?
Well, when we think of illness, we usually think of a foreign invader, like a virus or a bacteria, a pathogen entering the system.
Sure, something from the outside coming in?
Exactly. But the text emphasizes that cancer is fundamentally an information processing error. It is a corruption of the data in the vault itself.
Oh, wow. So if the physical molecule of DNA gets damaged, say maybe by radiation or some chemical exposure, the sequence of the code is permanently altered.
Yes.
And then when the cell tries to replicate, it just blindly copies that corrupted data.
Exactly. The replication machinery is perfectly faithful. It faithfully copies the error.
That's terrifying.
It is. And because the document establishes that fully understanding DNA's mechanism of action is the key to curing cancer, we can deduce why traditional treatments are just so difficult.
Right, because it's not a foreign body.
Exactly. You aren't just trying to kill a foreign cell. You are trying to halt a system that is operating exactly as it was programmed to do. It's just following a corrupted script.
But that brings up a really interesting mechanical problem, I think.
What's that?
Well, if DNA is this heavily guarded, double-stranded vault built for deep storage and stability, it can't exactly be out on the factory floor building things, right?
No, it's locked away.
Right. A hard drive doesn't build a computer by itself. So how does the data in the DNA actually become the physical tissues of the body?
That is precisely the role of the second nucleic acid, the RNA.
Okay, so the RNA is the missing link.
Exactly. While DNA is the permanent master record, RNA is the active messenger.
Got it.
Structurally, the text notes a few key differences that allow it to do this job. First off, it is single-stranded, which makes it much more flexible.
Right, not a rigid double helix.
Exactly. And it contains ribose sugar instead of deoxyribose, which subtly alters its chemical reactivity.
I was actually trying to visualize this process based on the text, and instead of thinking about it like, a CEO and a manager,
Right.
I started thinking about it more like an industrial 3D printing operation.
Oh, I like that.
Yeah, so the DNA is the proprietary digital CAD file locked on a secure server.
Safe and sound.
Exactly. But to actually make the part, that server has to transmit a specific temporary set of instructions down to the 3D printer on the factory floor. That transmission, that ticker tape of immediate actionable code, that is the RNA.
That's a highly accurate mechanical analogy, actually. The DNA carries the genes, which are essentially the master files, and it controls the synthesis of RNA.
So it builds its own messenger.
It literally transcribes its code into this single-stranded RNA molecule to transmit the genetic information out of the secure nucleus and into the cytoplasm of the cell.
And the document lays out a very rigorous 4-step pipeline for what that RNA ticker tape does next. It is incredibly systematic.
It's an assembly line.
It is. First, the cellular machinery receives the information from the RNA.
Right.
Second, it reads that specific sequence of bases. Third, it decodes what that sequence means.
Yeah.
And fourth, it uses that decoded information to direct the actual synthesis of new proteins. So it's receive, read, decode, use.
It is a totally flawless microscopic assembly line. The RNA is feeding the code into the ribosome, which in your analogy would be the nozzle of the 3D printer.
Exactly, the printer nozzle.
Right. And for every specific sequence decoded, it attaches a very specific physical molecule, an amino acid, to a growing chain.
But this introduces what feels like a terrifying vulnerability into the system.
How so?
Well, what happens when the original CAD file has a glitch?
Oh.
I mean, if the whole structural integrity of the body relies on this unbroken chain of information, from the secure vault to the ticker tape to the 3D printer, what if the original blueprint in the DNA is just wrong?
The source outlines a very sobering cascade of errors that answers that exact question.
I was afraid of that.
Yeah, it starts at the root. If errors are introduced into the genes carried by the DNA has no way of knowing it's wrong.
It just holds the data.
Right. It simply executes its function and synthesizes faulty RNA.
So the secure server automatically prints a corrupted ticker tape.
Precisely. And the cellular machinery down on the floor, the reader, it doesn't question the tape.
It just follows orders.
It receives, reads, decodes, and uses that faulty information to synthesize faulty proteins. It pulls the wrong amino acids and puts them in the wrong order.
And since biology is entirely dependent on physical shape, what actually happens when a protein is built wrong?
It experiences structural collapse.
Wow.
Because the physical structure of these newly synthesized proteins is incorrect, they literally cannot fold into the proper three-dimensional shape required to do their job.
So they're just broken right off the line.
Exactly. And the text is definitive on the consequence here. This specific sequence of errors is the root cause of genetic diseases.
It is just staggering when you really internalize that. A genetic disease isn't like a curse, it's a typo.
That's exactly what it is.
It is a...
Right. So the source text moves from the abstract information of nucleic acids to the highly tangible reality of proteins. It defines them chemically as nitrogenous compounds.
Okay, nitrogenous compounds.
But these aren't simple molecules like water or carbon dioxide. They are immense, staggering structures constructed from thousands of individual units.
The amino acids we mentioned earlier being stringed together by the RNA.
Yes. And the text specifically notes they are bound together by what are called peptide linkages.
Peptide linkages, okay.
Chemically, these are amide-amide bonds. You have to imagine thousands of these individual amino acid building blocks. covalently bonded end-to-end, forming a massive chain.
Like a giant necklace.
Exactly. But they don't just stay as a long string. The chemical properties of the different amino acids cause the entire chain to fold, twist, and crumple upon itself into a highly specific, intricate, three-dimensional geometry.
And what is the primary biological function of all this molecular origami?
Well, the text states that for human beings, these proteins are absolutely essential to form protoplasm.
Protoplasm. Which sounds like an archaic term, to be honest.
It does, but it simply refers to the living substance within a cell.
Okay, so like what?
The cytoplasm, the nucleus, the physical infrastructure that makes a cell an actual living, functioning entity rather than just, a microscopic bag of water.
Oh, I see.
Proteins provide the scaffolding, the transport tunnels, and mechanical gears of the cell.
So they are the literal architecture of our existence.
They are.
And because our bodies are constantly churning through them, like repairing cells and growing, we need a constant dietary influx of those raw amino acid building blocks.
Constantly, yes.
The document categorizes our dietary sources pretty straightforwardly. It lists animal sources like meat, specifically noting mutton, chicken, and fish, along with butter and eggs.
Right.
And then plant sources, pointing heavily to pulses and beans.
But the text also takes this really fascinating detour into how we've industrialized these structural molecules outside the human body.
Yeah, that part was wild.
It lists commercial uses for proteins that rely entirely on their tough, fibrous nature.
Yeah, it highlights the leather industry. I mean, when you really think about it, leather from animal hides is essentially just a massive chemically treated sheet of dense structural proteins.
That's exactly what it is.
And it also notes the bakery and food industry's heavy reliance on gelatin, which is a protein derived from collagen.
Right.
We are taking the structural scaffolding of biology and using it to make our shoes and thicken our desserts.
Which brings up a really crucial concept. If we are using these proteins for industrial and culinary purposes, it means we have figured out how to manipulate their physical structure. We know how to change their geometry.
This is exactly what I wanted to dig into, because the text outlines a laboratory skill that sounds incredibly sophisticated, but we literally do it in our kitchens every single day.
Yes, we do.
It's the process of denaturing.
Denaturing.
When I read this, I had to stop and really think about the mechanics of my own breakfast. Like, am I executing a complex thermodynamic denaturing of biological scaffolding when I just boil an egg on a Tuesday morning?
You absolutely are. You are performing macroscopic manipulation of microscopic architecture.
That is so cool. So walk me through the actual physics and chemistry of my breakfast. What is fundamentally happening when a protein denatures?
So the source defines denaturing as the precipitation or coagulation of a protein.
Coagulation, okay.
Let's go back to that massive chain of thousands of amino acids. Remember how we said it folds up into a very specific, intricate three-dimensional shape?
Right, the molecular origami.
Exactly. That shape is held together by relatively weak chemical forces, primarily hydrogen bonds and hydrophobic interactions.
So it's like a tightly wound ball of yarn, but held together by static electricity. It's delicate.
Very delicate. Denaturing is the process of destroying that specific folded shape without actually breaking the main chain of amino acids.
Oh, so you weren't cutting the yarn.
No, you are unfolding the yarn. And the text notes this can be triggered by altering the environment, either by radically changing the pH, making it highly acidic or alkaline, or, in the case of your breakfast, by applying heat.
And the text zeroes in on the egg as the perfect visual example for this. It explains that the clear, viscous fluid in a raw egg is a concentrated protein called albumin.
Exactly. In its natural, undenatured state, albumin proteins are folded up into neat little spheres that easily float around in water. That's why raw egg white is a fluid. But when you drop that egg into boiling water, you are flooding the system with intense thermal kinetic energy.
You are vibrating the molecules violently.
Oh, so violently that those weak hydrogen bonds holding the neat little spheres together just snap. The protein completely unravels.
Wow.
But it doesn't just stay unraveled.
Right, because now you have thousands of long, sticky strands of amino acids floating around in a chaotic, hot environment. They must crash into each other.
They crash into each other and they start bonding with each other instead of folding back on themselves.
Oh, I see.
They form a massive, tangled, chaotic net. This is the coagulation the text mentions.
So they link up.
Yeah, and this tangled net physically traps the water molecules, turning the fluid into a solid mass. And the reason it turns from clear to opaque white is because this new, dense, tangled molecular structure physically scatters light differently than the neat little spheres did.
That is absolutely wild. We are using thermal kinetic energy to permanently destroy the hydrogen bonds of a biological machine, forcing it to tangle into an opaque solid.
Yeah.
You really can't unboil an egg because you've caused a total chaotic architectural collapse.
And this really highlights how sensitive proteins are to their environment. But while some proteins just sit there and provide structure or get tangled up in boiling water, the text moves us to a completely different class of proteins that do the exact opposite of sitting still.
Right, some proteins are highly active, aggressive catalysts. And this leads us to the concept of enzymes. This is where the deep dive gets incredibly practical, I think. Because while our bodies rely on enzymes for every metabolic process, human engineering has completely weaponized these biological machines for commercial use.
It really is the ultimate form of biomimicry.
Yeah.
We observed how cells dismantle molecules, and we just scaled it up.
The prime example in the text, the one that completely floored me, is the detergent industry.
Oh, the laundry detergents, yeah.
We are literally putting microbes in our laundry rooms. The source details how commercial detergent powders and liquids are loaded with highly specific microbial enzymes designed to hunt down and destroy stains.
It is basically targeted biological warfare on your cotton shirts.
And it has to be targeted because enzymes are extraordinarily specific.
Oh, incredibly specific.
Yeah.
They operate on a lock and key mechanism. A specific enzyme has a physical shape and active site that only fits one specific type of molecule.
Let's look at the arsenal the text provides and figure out the mechanics of each weapon. First up on the list, lipases.
So, as the name suggests, lipases specifically target lipids, which are fats and oils.
Okay, so the grease stains.
Exactly. If you drop salad dressing on your shirt, that oil is hydrophobic. It repels the water to your washing machine. Soap alone struggles with it.
Right.
But lipases are designed to lock onto those fat molecules and chemically decompose them into smaller, water-soluble compounds.
They literally chop the fat into tiny pieces so the water can finally wash it away.
Okay, next on the list is amylase.
Amylase is engineered to target carbohydrates, specifically starch-based stains.
Like pasta sauce, gravy, mashed potato.
Yes. It locks onto the massive starch molecule and severs the bonds holding it together, turning it into simple, easily washable sugars.
That makes total sense. Then the text mentions cellulase, which, I gotta be honest, seems a bit counterintuitive to me.
Why is that?
Well, it degrades cellulose into water-soluble glucose, but aren't a lot of our clothes actually made of cellulose? Like cotton to cellulose, why doesn't the cellulase just eat my shirt? That's a brilliant deduction. It absolutely would eat the shirt if it were left unchecked.
Wait, really?
Yeah, but in commercial detergents, cellulase is used in highly controlled, minute quantities. Its job is actually fabric maintenance.
How does that work?
As cotton is worn and washed, tiny microfibrils of cellulose break loose on the surface, and they trap dirt and make the fabric look dull or pilled.
Oh, like when a shirt gets fuzzy and old looking.
Exactly. The cellulase enzymes act like microscopic lawnmowers. They shave off those loose, damaged fibers to release the trapped dirt and restore the smooth surface of the fabric without having enough time or concentration to degrade the main structural threads.
That is an insane level of chemical engineering happening while I'm just watching TV.
It is.
And finally, the text names bacterial proteases. Proteases destroy proteins.
Exactly. Blood, sweat, grass stains, or, that egg albumin you spilled at breakfast.
Egg again?
These are protein stains. They are incredibly tough because they bond fiercely to fabric fibers. The bacterial proteases hunt down the specific peptide bonds we talked about earlier and chemically dismantle them.
But wait, if proteases destroy proteins, what happens if I wash a wool sweater or a silk shirt? Those are made from animal hair and insect cocoons. They are pure protein.
That is precisely why every detergent bottle warns you not to use biological or enzyme-based detergents on wool or silk.
Oh, wow. Really?
Yes. The bacterial protease doesn't know the difference between the protein in a bloodstain and the protein making up your expensive wool sweater.
It just attacks.
It will lock onto the peptide bonds in the wool and begin digesting the fabric itself.
The microscopic assassins do not take prisoners. They just execute their chemical programming.
Literally.
Okay, but here's where my mind really started reeling. We just went through the intense biological warfare of the laundry machine. But as the text pivots, it turns out we are taking these exact same chemical assassins and putting them directly into our desserts. The food and beverage industry is entirely reliant on commercial enzymes.
It is the exact same molecular mechanics, just applied for culinary outcomes rather than cleaning.
Let's break down the examples from the text, starting with ice cream. The document highlights the use of the enzyme lactase. Now, I know lactase is what people who are lactose intolerant are missing, but why is the dairy industry deliberately adding it into commercial ice cream vats?
That's because of a really fascinating quirk in human taste receptors.
Oh.
Lactose is the natural sugar found in milk, but chemically, it is a complex sugar that doesn't fit very deeply into the sweet receptors on our tongue, so it doesn't actually taste very sweet.
Okay.
The industry adds the lactase enzyme to chemically cleave the lactose molecule in half,
And what are the two halves?
galactose and glucose. And the text points out the crucial reality here. Because of their physical molecular geometry, galactose and glucose fit much better into our taste receptors.
So they trigger a stronger response.
Exactly. They are objectively sweeter to the human palate than the original lactose.
That is a brilliant biochemical hack. By just dropping a protein catalyst into the milk, it snips the sugar in half, and you naturally get a sweeter ice cream without having to dump in loads of extra external cane sugar.
Exactly. It improves the flavor profile purely through enzymatic action.
Okay, what about baking? We just talked about amylase being used to dissolve pasta stains off my shirt. The text says we put that same enzyme in bread dough.
We do. Flour is primarily starch, which, as we established, is a massive, tasteless molecule.
Right.
When you add amylase to the dough, the enzyme acts as a predigester. It attacks the starch in the flour, yielding more usable material, but critically, it converts some of that tasteless starch directly into sweet glucose syrup, right there in the mixing bowl.
So the enzyme is artificially accelerating the breakdown of the flour to create a natural internal sweetener.
Yes, and that glucose doesn't just taste good, it provides immediate, easily accessible food for the yeast.
Oh, to help it rise.
Exactly, which greatly improves the rise in the overall bread-making process.
Incredible. Next example from the source. Fruit juices. I always assumed making grape juice just meant, like, crushing grapes and filtering out the seeds. But the text says enzymes are a required step.
Squeezing a grape leaves you with a lot of suspended structural plant material,
Right.
specifically pectin. It makes the juice cloudy and thick.
Right.
When enzymes like pectinase are added to the crushed fruit, they go to work dismantling that structural webbing. And the text outlines 3 massive commercial benefits to this. First, it completely removes those suspended particles, resulting in a perfectly clear juice.
Which is what consumers expect visually. We don't want cloudy juice.
Exactly. Second, by breaking down the cellular walls of the fruit that would normally trap the liquid, the enzymes dramatically increase the total yield of juice extracted per ton of grapes.
More juice for the same amount of fruit.
Yes. And third, the breakdown of the skins allows for a far better, deeper extraction of the natural colors. Clearer juice, more juice, and better-looking juice, entirely driven by enzymatic degradation.
And then, of course, the text touches on the oldest commercial use of microbiology in human history, alcohol fermentation.
The foundation of civilization for some historians.
Yeah, the text explicitly points out that fermentation isn't just yeast doing magic. Yeast is simply a biological delivery mechanism packed with specific enzymes.
That's all it is.
And the text names 3 of them: diastase, invertase, and zymase. We use these yeast enzymes commercially for the fermentation of carbohydrates like molasses and starch.
Those enzymes execute a really complex chemical cascade. They take the sugars and fundamentally alter their molecular structure, stripping off carbon dioxide and leaving behind ethanol.
So no enzymes, no alcohol industry.
None whatsoever.
Finally, rounding out the food section, the text notes the broader dairy industry. Beyond the lactase trick for ice cream, enzymes are the absolute foundation of cheese and yogurt production.
Right? Think about rennet. It's the enzyme complex used for centuries to make cheese.
Oh, I've heard of rennet.
Yeah, it acts on the milk proteins, causing them to curdle and separate from the liquid whey. Without these highly specific catalysts, we just couldn't produce the vast array of textures and flavors in the dairy aisle.
It is stunning to realize that whether we are fighting stains or fermenting wine, we are just harnessing the exact same microscopic lock and key mechanisms.
It's all the same tools.
But this perfectly transitions us to the next vital question. We know enzymes like amylase and lipase are sent in to break down starches and fats.
Right.
But what actually are those target molecules? If we look at the fuels and structural components of biology, we need to deeply examine carbohydrates and lipids.
Okay, let's begin with carbohydrates. The source text gives us a rather intimidating chemical definition right out of the gate. It calls them polyhydroxyaldehydes or ketones.
Okay, polyhydroxyaldehydes or ketones. I
I
mean,
know.
if you don't have a degree in organic chemistry, that just sounds like random syllables. Let's translate that into actual mechanics. What does that mean for the structure of the molecule?
Let's break the word polyhydroxy down. Poly means many, and hydroxy refers to a hydroxyl group, which is an oxygen atom bonded to a hydrogen atom.
Okay, simple enough.
So a carbohydrate is basically a chain of carbon atoms, and hanging off almost every single carbon in that chain is one of these oxygen-hydrogen groups.
Why does that matter?
Because oxygen and hydrogen don't share electrons equally. The oxygen hogs them, making it slightly negative, while the hydrogen becomes slightly positive. This is called polarity.
Polarity, right?
And you know what else is highly polar? Water.
Ah, so because carbohydrates are covered in these polar hydroxyl groups, water molecules are incredibly attracted to them.
Exactly. It makes carbohydrates highly hydrophilic, or water-loving. This is the fundamental chemical reason why most sugars dissolve so easily in water.
That makes total sense.
They're naturally synthesized macromolecules, acting as the main source of energy for the body, and their polarity allows them to be easily transported through our water-based bloodstream.
And the text notes, we get them primarily from plants, fruits, vegetables, cereal crops, and from milk. But to really grasp how they work, the source provides a concept diagram that breaks them down into 3 classifications.
Right, 3 main types.
I was looking at this, and a visual analogy really helped me. Think of carbohydrates like a massive box of Legos.
Okay, Legos.
You have your individual single Lego bricks, then you have small pre-assembled kits of a few bricks snapped together, and finally you have massive towering Lego castles made of thousands of pieces.
That maps perfectly onto the 3 categories that text provides, actually. Let's look at the single Lego bricks first, the monosaccharides.
The text states these are made of 3 to 9 carbon atoms and are unhydrolyzable, meaning what exactly?
Well, hydrolysis is the process of using water to break a chemical bond. Unhydrolyzable simply means this molecule is the fundamental base unit.
You can't break it down further.
Right. You cannot use water to break it down into a smaller carbohydrate. It is the single brick.
And their physical properties. The text says they are sweet, they are crystalline solids, and as we just established with the hydroxyl groups, they are highly soluble in water.
Right. The key examples the text provides are glucose, fructose, and galactose. You find these simple, fast-acting energy bricks in things like honey and ripe fruits.
Because they were already broken down to the base unit, your body absorbs them immediately.
Exactly, causing a rapid spike in blood energy.
Okay, so if we take a few of those single bricks and snap them together, we get the small kits, the oligosaccharides.
Yes. When you perform hydrolysis on an oligosaccharide, when you force water in to break the bonds holding the bricks together, the text notes they yield between 2 to 9 individual monosaccharide units.
But chemically, they behave very similarly to the single bricks, right?
They do. The text confirms they are also sweet, they form crystalline solids, and they are easily soluble in water. Your body just has to do one quick step of chemical snipping to break them into single bricks before absorbing them. The examples here are sucrose, which is common table sugar, along with lactose from dairy and maltose. We source these heavily from sugarcane and sugar beets.
But then we reach the third category, and the properties change drastically. The massive Lego castles, the polysaccharides.
These are the heavyweights of the carbohydrate world. Polysaccharides consist of hundreds, sometimes thousands, of monosaccharides bonded together in massive, complex macromolecules.
And because the molecule is so enormous, the physics completely shift. The text highlights a stark contrast here. Polysaccharides are tasteless. They are amorphous solids instead of crystalline, and crucially, they are insoluble in water.
Let's look at the mechanics of why that happens. Why is a massive sugar suddenly tasteless?
Yeah, why?
Well, taste is just a chemical locking into a receptor on your tongue. Monosaccharides and oligosaccharides are small enough to perfectly slide into the sweetness receptors.
But a polysaccharide
Is like trying to park an aircraft carrier in a compact parking space. It physically cannot interact with the receptor, so your brain registers no sweetness.
That's a great visual. And the insolubility. If they still have all those polar hydroxyl groups, why doesn't water dissolve them?
Because in these massive structures, there are so many hydroxyl groups in such close proximity that they start hydrogen bonding aggressively with each other.
Oh, they bond internally.
Exactly. They form tight, incredibly strong internal networks. The water molecules just can't penetrate the fortress to pull it apart.
The examples the text gives for these massive structures are starch and cellulose, which we get from cereals and crops. And speaking of that insolubility, the document offers another brilliant kitchen science observation.
I love these practical examples.
Right, you can physically prove the structural difference between these molecules using just a glass of water.
It explicitly notes the contrast between the solubility of starch and sugar.
Yes, if you take a spoonful of sucrose, an oligosaccharide, a small kit of Legos, and stir it into water, the water molecules easily surround the small structure, pull it apart into solution, and the water stays perfectly clear.
Right.
But if you take a spoonful of cornstarch, a massive polysaccharide castle, and stir it into a glass of water, it refuses to dissolve. The water just turns cloudy, and eventually, the massive, heavy starch molecules just sink and settle at the bottom.
It is a macroscopic visual proof of molecular size.
It connects the abstract chemistry directly to your physical reality. And, while we tend to demonize carbs in modern culture, the text specifically lists the profound health benefits of these molecules.
We really need them.
Beyond just raw caloric energy, they are required to regulate sugar levels in the blood. The complex ones aid significantly in digestion. They actually help lower cholesterol levels, and they protect the body's muscles from cramping.
Which brings us to the other major energy source covered in this section, the biological batteries.
Lipids, fats, and oils. The text provides a rigorous chemical definition here. Lipids are macromolecules made up of long-chain carboxylic fatty acids. Specifically, it describes them as esters of fatty acids combined with glycerol.
Let's unpack that geometry. A lipid is basically a backbone of glycerol with 3 long tails of carbon atoms hanging off it.
Okay, a backbone with 3 tails.
And the text notes these tails can be either saturated or unsaturated. What is the physical difference between a saturated fat and an unsaturated fat?
Yeah, you hear those terms all the time.
It all comes down to the shape of the tail. A saturated fatty acid has single bonds between all its carbon atoms, meaning the tail is perfectly straight.
Perfectly straight.
Because the tails are straight, the molecules can pack together very tightly. This tight packing means that at room temperature, saturated fats like butter or animal fat are solid.
But an unsaturated fat has double bonds in the carbon chain.
Yes, and structurally, a double bond creates a rigid kink or bend in the tail.
Oh, so they aren't straight anymore.
Right. Because the tails are bent and crooked, the molecules cannot pack tightly together. There's too much empty space between them. Therefore, at room temperature, unsaturated fats remain liquid. We call them oils.
Structure dictates state. It's fascinating. And the text states these are high-in-energy compounds synthesized across the board by animals, plants, and microorganisms. But much like proteins, lipids aren't exclusively for eating. The document notes their massive industrial applications.
Beyond high-energy food, lipids are the absolute foundation of the soap industry.
How does fat become soap?
Through a process called saponification. You take these lipids, these triglycerides, and boil them with a strong alkali, like lye.
Okay.
The extreme pH breaks the ester bonds connecting the tails to the glycerol backbone. The free fatty acid tails react with the sodium from the lye to form a salt. That salt is soap.
And how does that clean things?
One end of the molecule loves water, the other end loves oil, allowing it to bridge the gap and wash grease down the drain.
Again, industrial chemistry relying on fundamental biological mechanics. The text also notes lipids are crucial in the manufacturing of various medicines, acting as delivery vehicles for drugs that can't dissolve in water.
Right.
So looking at our roadmap, we've covered a massive amount of ground. We have the genetic data in the DNA. We have the physical structural proteins. We have the active enzyme catalysts cutting molecules apart. And we have the high-energy fuels in carbohydrates and lipids.
It's quite the list.
On paper, it looks like a complete functioning system.
It seems like all the necessary components for life are there. But as the text pivots into our final topic, it highlights a historical realization that something critical was missing.
We had the engine, the frame, and the gas, but the car still wouldn't run. And that brings us to the essential accessory factors, which we know today as vitamins.
The source text gives us a really important historical anchor here. It notes that back in 1912, a scientist named Hopkins made a crucial observation through dietary experiments.
What did he find?
He found that even if an animal was given a perfectly formulated diet consisting of pure carbohydrates, proteins, and fats in the exact right ratios, normal growth was impossible. The animals would sicken and fail to thrive.
There was an invisible X factor required to make the chemistry actually happen.
Exactly. Hopkins deduced that there were unknown substances, required only in trace amounts, that were absolutely critical for the machinery to function. He called them accessory growth factors.
Which is a very literal descriptive name, but thankfully another scientist realized they needed better PR.
Yes, the text credits a scientist named Funk, who later proposed the term vitamin. Funk is also specifically credited in the document with discovering vitamin B1, also known as thiamine.
So, mechanically, what is a vitamin? Why were they the missing piece of the biological puzzle?
The defining characteristic of a vitamin, as the text explicitly states, is a negative one. Our bodies are unable to synthesize them.
We can't make them at all.
No. Evolutionarily, we either lost the metabolic pathways to produce these complex organic molecules, or we never had them. But our cellular machinery evolved to rely on them to regulate our metabolism.
Which means we are entirely precariously dependent on our environment to get them.
We must supply them to our bodies, either directly through our diet by consuming plants and animals that can synthesize them, or through modern dietary supplements. They are the regulatory keys that allow the enzymes, proteins, and carbs to interact properly.
Now, regarding how we get them, I want to zero in on a fundamental rule highlighted in the text. It's a mechanical reality of how vitamins work that modern supplement culture often completely ignores.
Oh, this is a big one.
The text boldly states that vitamins cannot be assimilated without ingesting food.
This is perhaps the most practical takeaway in the entire document.
It literally says, this is why it is suggested that vitamins must be taken with a meal. You can't just wake up, swallow a handful of expensive multivitamin pills with a glass of tap water on an empty stomach, and expect to be healthy.
You are literally flushing your money down the drain.
Why? Because of the mechanics of assimilation. Without the presence of dietary fats, carbohydrates, and the active enzymatic digestive processes triggered by a real meal, the vitamins have no transport mechanisms to get across the intestinal wall into the bloodstream.
It is a system of codependence. And to fully grasp how these vitamins interact with our bodies once they do get inside, the text divides them into two major categories based on their chemical solubility: water-soluble and fat-soluble.
Let's analyze the mechanics of these two camps, starting with the water-soluble vitamins.
As the name indicates, these are vitamins with chemical structures that readily dissolve in water, much like the simple carbohydrates we discussed earlier.
Right.
The text lists two main entities here: the B complex, which it knows is actually a group of 10 different distinct vitamins and vitamin C, also known as ascorbic acid.
And because they are water-soluble, our bodies handle them in a very specific way.
Dramatically different from the other category. Because human blood and urine are water-based, the transport and removal of these vitamins is seamless.
Oh, I see.
The text points out that water-soluble vitamins are rapidly excreted from the body. Your intestines absorb what your cells immediately made for metabolic regulation, and the rest is filtered by the kidneys and flushed out in your urine within hours.
Which gives them a very safe physiological profile.
Exactly. The text emphasizes a key medical reality. Because they are so rapidly excreted, these water-soluble vitamins are not toxic, even if they are taken in remarkably large quantities. Your body simply refuses to hold on to the excess.
Okay, but this is where I want to push back hard against a really dangerous assumption. Because water-soluble vitamins are safe, people apply the logic of more is better to all vitamins.
Yeah, that's a mistake.
If you feel a little run down, you take a massive megadose of every letter in the alphabet. But this source text issues a massive explicit warning about the other category, the fat-soluble vitamins.
And ignoring that warning can have devastating structural consequences for the body. The fat-soluble vitamins are vitamins A, D, E, and K. Mechanically, these molecules do not dissolve in water. They only dissolve in lipids.
Which means when the kidneys try to filter the blood, they can't grab these molecules and excrete them in the urine.
No, they cannot. The text warns that if these fat-soluble vitamins are taken in large quantities, they accumulate.
They just build up.
Because they dissolve in fat, your body stores the excess deep within your lipid tissues and your liver. They build up over time. And this accumulation, this hypervitaminosis, causes severe diseases.
The document provides a specific, terrifying example of this toxicity. It states that the accumulation of too much vitamin D in the body causes bone pain and bone-like deposits in the kidney.
Think about the mechanics of that. Vitamin D regulates calcium.
Right.
If you flood your system with massive unnatural doses of fat-soluble vitamin D, it accumulates in your tissues and signals your body to aggressively pull calcium from your blood and deposit it where it shouldn't be.
Oh, wow.
It literally begins forming calcified, bone-like structures inside the soft tissue of your kidneys. It is a stark reminder that vitamins are not just benign health dust. They are incredibly potent biochemical regulators.
Balance is absolute law here, because as the text immediately follows up, while toxic accumulation is dangerous,
Yeah.
a deficiency of these exact same vitamins also causes severe structural failure.
We were walking a tightrope. Let's examine the detailed breakdown the text provides for two of these crucial, yet potentially dangerous, fat-soluble regulators, vitamin A and vitamin D.
Let's start with vitamin A. What are our dietary sources?
The source lists animal-based lipids, dairy products, eggs, oils and fats, and fish, but it also notes a vital plant precursor, beta-carotene.
Oh, like in carrots.
Yes. You find beta-carotene in green vegetables, carrots, and it's heavily stored in animal liver. When you consume beta-carotene, your body uses an enzyme to cleave the molecule in half, producing active vitamin A.
And what is its specific mechanical job in the body?
The text highlights two primary functions. First, it is responsible for maintaining the health and structural integrity of the epithelium.
What's the epithelium?
That's the cellular covering of all internal and external surfaces of the body, from your skin to the lining of your lungs.
Ah.
But its second function is even more specific.
Yeah.
It acts directly on the retina's dark adaptation mechanism.
It provides the chemistry required for us to see in the dark.
Exactly. It is a core component of rhodopsin, a light-sensitive receptor protein in the eye. When a photon of light hits rhodopsin, the vitamin A molecule literally changes its physical shape, triggering an electrical signal to the brain.
And the text clearly outlines the disease caused by its deficiency, night blindness and severe eye inflammation.
Right.
If you are missing that specific fat-soluble molecule, the physical mechanism in the retina cannot reset. The hardware is there, but the chemical trigger is gone, and your vision degrades.
It perfectly illustrates how a microscopic molecular deficiency results in a macroscopic sensory failure.
Okay, let's look at vitamin D, the one capable of causing kidney calcification if you take too much. Where do we safely source it?
The dietary sources listed are fish liver, dairy products, oils, and fats. But vitamin D possesses a highly unique, almost plant-like mechanism for sourcing. The text states that vitamin D is formed directly in the skin when it is exposed to sunlight.
I always found that incredible. We literally photosynthesize our own vitamins.
It is a brilliant evolutionary adaptation. The ultraviolet radiation from the sun penetrates the skin and physically breaks open a specific cholesterol ring stored in the dermal tissues. That broken ring is the synthesized vitamin D molecule.
And what is its vital role in the system?
The text establishes that vitamin D has a critical role in the absorption of calcium from our intestines. And calcium, of course, is the rigid mineral essential for the maintenance and structural integrity of healthy bones.
So it's a gatekeeper.
Exactly.
It doesn't matter if you drink a gallon of milk a day and consume massive amounts of calcium. If you are deficient in vitamin D, your intestines simply cannot absorb the mineral.
Precisely. The lock is there, but the vitamin D key is missing. The dietary calcium just passes right through you.
And the physical consequence of this deficiency.
As noted by the text, it's rickets, a devastating condition characterized by weak, soft, and deformed bones, particularly in growing children who lack the structural rigidity to support their own body weight.
So looking back at the entire landscape we've mapped out today, vitamins are these incredibly potent, externally sourced chemical regulators.
Yes.
They are the final piece of the puzzle that ensures the proteins fold correctly, the enzymes catalyze effectively, and the carbohydrates and lipids are burned for fuel in a controlled manner.
They are the micromanagers of the metabolic engine, ensuring the entire biochemical symphony stays in rhythm.
And with that, we have reached the end of our deep dive into 112116.pdf. We have traced an unbelievable journey through the invisible architecture of life.
It is a remarkable synthesis of information. It forces you to realize that biology isn't magic. It is highly complex, incredibly precise, applied chemistry.
Just to summarize the incredible scale of what we've explored today, we started inside the heavily guarded vault of the cell, looking at the immense double-stranded stability of DNA and how its single-stranded messenger, RNA, acts as a ticker tape for the cellular 3D printers.
Right.
We saw how a single glitch in that code results in a misfolded protein, leading to structural collapse and genetic disease like cancer.
We then examined those proteins, the literal building blocks of our protoplasm. And we discussed the thermodynamics of denaturing, how simply applying heat breaks delicate hydrogen bonds, tangling the molecules into a solid, opaque mass, completely changing the physical state of an egg.
From there, we uncovered the hidden world of active enzymes, the hyperspecific biological catalysts operating on lock and key mechanisms. We saw how human engineering harnesses bacterial proteases and lipases as microscopic assassins to hunt down stains in our laundry.
Right, the laundry enzymes.
And how we use amylase and lactase to chemically alter the sweetness and structure of our bread, our juice, and our ice cream.
Then we analyzed the complex architecture of our biological fuels, understanding why the polar hydroxyl groups make carbohydrates water-soluble, and how massive polysaccharide structures like starch are simply too big to trigger a sweetness response on our tongues.
We contrasted this with lipids, observing how the physical kink of a double bond determines whether a fat is a solid butter or a liquid oil at room temperature.
And finally, we uncovered the delicate, dangerous balance of the accessory growth factors, the vitamins.
We learned the crucial metabolic rule that they must be taken with food to be assimilated, and we explored the razor-thin margin between deficiency and toxic accumulation with fat-soluble regulators like vitamin D.
It is a system of immense complexity, yet driven by very clear, understandable thermodynamic and chemical laws.
It really is. Now, as we wrap up today's exploration, I want to leave you, the listener, with a final provocative thought to mull over. Something that connects two seemingly entirely separate concepts from the source text we just unpacked.
So I'm intrigued. What's the connection?
Well, early on, we learned that genetic diseases are fundamentally caused by typos in the DNA, which lead the RNA to synthesize faulty proteins. These proteins misfold, fail to function, and cause cellular collapse.
Right.
But then, later on, we learned that humanity has mastered the commercial use of bacterial proteases, specific enzymes engineered to hunt down, lock onto, and completely dismantle protein bonds to remove stains from our clothes.
Okay, I see where you're going with this.
So think about this. What if the future of curing genetic disorders isn't just about the impossibly difficult task of trying to go into the genetic vault and rewrite the original DNA code?
Right.
What if instead we utilize the exact same biochemical principles as the enzymes in our laundry detergent? What if we engineered bespoke, highly targeted medical proteases, injected them into the bloodstream, and programmed them to hunt down, lock onto, and safely dissolve those specific faulty proteins before they can cause any structural harm to the body?
Using the exact chemical mechanisms of commercial stain removal as a blueprint for advanced intracellular medical therapies. It's a profound extrapolation.
Right.
You aren't fixing the broken printer. You are just deploying microscopic sweepers to instantly dissolve the bad parts as soon as they drop off the assembly line.
It makes you wonder what else is possible once you stop looking at the surface and start understanding the invisible machinery. Thank you all so much for joining us on this deep dive into the microscopic world of biochemistry. We hope this conversation encourages you to think a little differently, to see the hidden complexity and the brilliant chemical engineering in the world around you. The next time you boil an egg, throw a load of clothes in the wash, or just step outside to feel the UV radiation synthesize vitamins in your skin. Until next time, keep diving deep.